Hello everyone, and welcome to chapter 13.8, where we will be going over Jacobians and change of variables. So first, for the warm-up, we'll just evaluate this very simple determinant. It should only take you a couple of seconds. Alright, let's go through it. So to find a determinant, all we have to do is take the product of these two numbers and subtract the product of these two numbers. So what we'll get is 2 times 3 minus 1 times 1, which is just equal to 5. Now we'll go ahead and give the definition of a Jacobian. So the definition of a Jacobian is as follows. If x is a function g of u and v and y is a function h of u and v, then the Jacobian of x and y with respect to u and v is denoted as partial of xy over partial of uv, and it's the determinant of the matrix dx du, dx dv, dy du, and dy dv. Of course, they're all partial derivatives, and this would also be equal to partial x partial u times partial y partial v minus partial y partial u times partial x partial v. And now we'll move on to example 1. Find the Jacobian where x is equal to 2u plus v and y equals to u plus 3v. So all you have to do is use the formula that we just defined, and it should be pretty simple. Alright, so we'll go ahead and go over it. So we'll start off by defining the Jacobian, which is partial xy over partial uv. And this will be equal to the determinant of partial x partial u, partial x partial v, partial y partial u, and partial y partial v. So next we can evaluate this by plugging in each of these partial derivatives. So we would have partial x partial u, which is equal to 2, partial x partial v, which is equal to 1, partial y partial u, which is equal to 1, and finally partial y partial v, which is equal to 3. And this is the same determinant as the one we had in our warm-up, so we can just get the answer of 5. Alright, so now we'll do another example, except this time x is equal to r cosine theta and y is equal to r sine theta. So go ahead and pause this one and try to figure it out. Alright, so we'll go ahead and go through it. So the difference this time is we have the variables r and theta instead of u and v, but they represent the same things. So we can say partial of xy over partial of r theta is equal to the determinant of partial x partial r, partial x partial theta, partial y partial r, and partial y partial theta. So then we can go ahead and evaluate this. So partial x partial r would be equal to cosine of theta. Partial x partial theta would be equal to negative r times sine of theta. Partial y partial r would just be equal to sine theta. Finally, partial y partial theta would be equal to r times cosine of theta. So then we can go ahead and evaluate this determinant. So we get r times cosine squared of theta plus r times sine squared of theta, which will just give us r as our answer. Now we'll quickly go over something called transformations, and it's more of just a notation thing that's not very big. So if s is in the uv plane and r is in the xy plane, a change of variables to transform s into r is given by the transformation of uv, which is equal to xy, which is equal to g of uv and h of uv. We'll see how this works in the next example. Example 3. Let R be a region bounded by x minus 2y equals 0, x minus 2y equals negative 4, x plus y equals 4, and x plus y equals 1. Find a transformation T from region S to R such that S is a rectangular region. Alright, let's go through it. So what we essentially want to do is find x and y that are both functions of u and v, such that u and v form a rectangular region. So the easiest way to do this is to let u equal to x plus y and let v equal to x minus 2y. Next, we can solve for x and y in terms of u and v like a standard system of equations. So we have u equals to x plus y and v equals to x minus 2y. If we take the first equation and subtract the second, we'll get y equals to 1/3 times u minus v. If we take 2 times the first equation and add it to the second, we'll get that x is equal to 1/3 times 2u plus v. And that's pretty much all there is to it. So we can write x and y equal to the transformation of u and v, which is equal to 1/3 times 2u plus v and 1/3 times u minus v. Then as a result, our new bounds are v equals 0, v equals -4, u equals 4, and u equals 1. We can plot the graph of S as shown here, and it is a rectangular region. And now we'll go over the main theorem of this chapter, which is theorem 13.5, change of variables. So let R and S be regions in the x, y, and uv planes where x is a function g of u and v, and y is a function h of u and v, such that each point in R is the image of a unique point in S. If f is a continuous function on R, g and h have continuous partial derivatives on S, and the Jacobian partial xy partial uv is non-zero on S. Then the double integral of f of x and y dx dy is equal to the double integral of f of g of u and v and h of u and v times the Jacobian and du dv. We won't be going over the proof for this theorem, but instead I'll show you an animation which should highlight why it works. So recall all the way back in linear algebra where we went over the concept of linear transformations. Essentially, a matrix which represented this linear transformation would stretch or squish the space depending on its values. Also recall that the determinant of a linear transformation would be the factor in which it stretches its area. So we can watch this animation as the matrix 3, 1, 0, 2 stretches these two basis vectors so that it becomes a parallelogram. Now we also introduce a concept called local linearity. So essentially what this says is at a very, very small level, which is indicated by our partial derivatives, the transformation is essentially linear for any spot on the plane. So when we go ahead and watch the animation here, we'll see this very, very small area indicated by this square and its zoomed up version on the right side. We'll see that this spot remains relatively linear even after this non-linear transformation is applied to it. And as we can see, it is a parallelogram, which is the result of a linear transformation. What we get out of this is a matrix full of these partial derivative values that represent this stretch or squish of this parallelogram. And then when we apply this to a double integral, it allows us to change the variables. Now let's quickly revisit example 2. So what we did was we found the Jacobian for x equals r cosine theta and y equals r sine of theta, and we found out that it was just r. So if we look at what we learned a couple sections ago in section 13.3, to transform something from rectangular form to polar form, what we did was we had to add this extra r term, which we weren't sure about before. So now we can see that that is the Jacobian term, and this is essentially derived from the theorem 13.5. That would be it for now, and Andrew will go over examples in the next video. Hopefully you guys are having a good break, and I can't wait to see you soon.